Hello students, welcome to my YouTube channel Integrated Physics Studies IPS. एथरे मु ऑलरेडी प्लस 2 सेकंड ईयर सिलेबस कंप्लीट कर सारछि एबे मु प्लस 3 CBCS ऑनलाइन क्लासेस रो वीडियोस गुडा अपलोड करिवि जदि भल लागिला ताले लाइक कर देबो एवं सब्सक्राइब कर देबो जो वीडियोस गुडा मु अपलोड करिवि तार नोटिफिकेशन पई एठी बेल आइकन को ऑल रे सेट कर देबो गोटे इंपोर्टेंट जिंस वीडियोस रो ऊपर एठी जो 3 डॉट्स देखुछो तार क्वालिटी एठी देखो बाय डिफॉल्ट 360 अछि तमे ताकू पढे मध्ये परिबो एठी एडवांस रे क्लिक करी तमे रिजोल्यूशन बढ़े परिबो प्रति वीडियोज रे मु पीडीएफ लिंक देबी ताकू एठी ड्रॉप डाउन लिस्ट रो तमे क्लिक करी डाउनलोड मध्ये करि परिबो पीडीएफ को लास्ट रे एठी जो मोर चैनल नेम अछि याकू क्लिक करी तमे एठी प्ले लिस्ट को जाई मु प्रति वीडियोज को यूनिट वाइज एज पर सिलेबस सजाई की रखिथिबी तमे सर्च करि परिबो ओके थैंक यू हेलो स्टूडेंट्स आज रो टॉपिक रे हमें एटॉमिक स्पेक्ट्रा विषय रे पढिबा सो वी नो दैट whenever we excite a substance in atomic state, then we observe a line spectrum. Okay, that is why it is also called atomic spectrum, right? Now fine spectral lines will correspond to definite energy, and hence it is the importance of this line spectra. Suppose for example we take mercury vapor. Now when this mercury vapor is excited in the atomic state, then its atoms will absorb only definite amount of energies. For example, when mercury atoms will absorb 4.86 electron volt of energy, then they will be excited from the ground state to the first excited state, and they remain in this first excited state for a short period of time, and thereafter they will return back to their normal state, that is the ground state. Okay, so in this process of emission we will have photons, each of energy 4.86 electron volt, which is the same energy as absorbed while going from ground to first excited state. Okay, now similarly in case of second, third and fourth excited states, the mercury will correspond to energy of 6.67, 8.84 and 10.4 electron volt respectively. So if energy more than 10.4 electron volt is given to the mercury atoms, then they will be ionized. Okay, now in returning back to the ground state, that is the normal state, again from second, third and fourth excited states, the mercury atoms will emit the photons of energy that is same as 6.67, 8.84 and 10.4 electron volt respectively. Okay, so the energies of these excited states will be like 4.86, 6.67, 8.84 and 10.4 electron volt. Okay, for the mercury atoms in the first, second, third and fourth excited state. Okay, so we can plot an energy level diagram, and in general we say that the energy of the ground, that is the normal state, which is denoted by E0. Okay, and the first, second and third excited states like E1, E2, E3 and so on. Okay, so for the sake of simplicity in calculation, let us consider that the ground state energy E0 is equal to 0. Otherwise the electrons will have some energy in the ground state. Okay, so you can see this is the figure which is showing the energy level diagram. So in the left side we have the emission of photons from the excited state to the ground state, that is from E1, E2, E3 to E0. Okay, now in the right side we have the excitation from ground state to the excited state, that is from E0 to E1, E2 and E3. Okay, so the energies E0, E1, E2, E3 are here shown in the figure, and the emission of energy by an atom takes place because of transition from higher to lower energy state, as shown by the down arrows in the left side figure, and hence the first figure, that is on the left side, will represent the emission spectrum in terms of energy level diagram. Now although other transition from E2 to E1, then E3 to E1, then E3 to E2 are also possible. As you can see, these are shown by the dotted line. Okay, these are the other types of transition, right? So these are also possible, and in case of mercury, the excited states having energy 4.86, 6.67, 8.87 and 10.4 electron volt will correspond to frequencies which lie in the violet and ultraviolet regions. Okay, now the visible mercury spectrum is seen because of the transition from higher to lower excited state, that is from E2 to E1, then E3 to E1, and so on. Now in the second figure that we have seen in the right side, the arrows from lower to higher energy excited states will represent the absorption of energy. Okay, and in this case the energy which is absorbed is equal to the difference of energy between the two states, that is the difference E1 minus E0, E2 minus E0, E3 minus E0, E2 minus E1, E3 minus E1, E3 minus E2, and so on. Okay, so the absorption of energy here is also quantized discrete phenomena. Now let us proceed further. When light from a source giving continuous spectrum in order to pass through a vapor in atomic state, then the transmitted light will show dark lines. But however, these dark lines are also exactly present at the same places of lines that are being emitted by the absorbent. Okay, and it should be noted that all the lines in the emission spectrum of the element are not observed in case of the dark lines because of the difference in the physical condition of the substance at the time of emission and absorption. Now suppose during both emission and absorption spectra, if the wavelength which is corresponding to energy transition between the two states, that is say E minus E0 is lambda. Okay, so lambda jodi wavelength hegala, then E minus E0 will be given by h nu, where nu is the frequency, h is the Planck's constant, so this is also equal to hc by lambda. C is the velocity of light, and here E and E0 are the energy of the excited and the normal, that is the ground state of the atom. Okay, so that the wavelength lambda will be given by hc by E minus E0. Okay, so this is all about the atomic spectra.
Thank you.